All right, calculus students, today we're looking at FRQ number 5. As always, make sure you complete the FRQ before watching the video. So let's go ahead and get started. Train A runs back and forth on an east-west section of railroad track. Train A's velocity, measured in meters per minute, is given by a differentiable function v of a, or v sub a of t, where t is measured in minutes. Selected values from v sub a of t are given in the table above. So this is the velocity of the train at certain times. Okay, so find the average acceleration of the train over the interval from 2 to 8. The first thing we need to consider, we know we're going to do one of our average functions, either average value or average rate of change. So our question is, how does acceleration relate to velocity? Well, acceleration is the rate of change of velocity. So what this is asking for, it's saying find the average rate of change of velocity of the train. Well, average rate of change, well, that is, in this case, v of 12 minus v of 0 over 12 minus 0. Oh, sorry. It says from 2 to 8. So we need to be a little more specific. So that's going to be v of 8 minus v of 2 over 8 minus 2. Much better. And then we just plug it in. So v of 8 is negative 120. V of 2 is 100 over 8 minus 2. So negative 120 minus 100 is negative 220. 8 minus 2 is 6 over 6, which simplifies down to about negative 110 over 3 meters per minute squared. This is all we needed for this part, and this is only 1 point. Okay, move to the next part. Part B. Do the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some time from 5 to 8? Okay, so does the information in the table guarantee that train A's velocity is negative 100 meters per minute at some point from 5 to 8? So let's start by thinking about the original equation. This is differentiable. Now, if it is differentiable, since v sub a is differentiable, that automatically tells us it's continuous. Because it tells us it's a differentiable function, that means it has to be continuous. Okay? Now, if it just said continuous, that doesn't mean it's differentiable, but to be differentiable, you have to be continuous. So, let's look at what's happening. We know that at the velocity at 8, we know that that is negative 120. And then we know the velocity at 5 is 40. And we know that between these 2 points, it is continuous. So the question is, somewhere in between these 2 points, is the velocity going to be negative 100? And that's true. That has to happen because we know it's continuous, which means it has to cross every value. So there's a specific theorem we can reference here. By the intermediate value theorem. Very old theorem, but by the intermediate value theorem, there is a time t from 5 to 8 where v of t is equal to negative 100. Pretty straightforward. It's just making sure you remember the IVT. If it's continuous, it has to cross everything in between those 2 points. This is 2 points though. 1 point for saying this part right here in some way. So this part is 1 point. And then 1 point for your justification with IVT. So the justification with the IVT, let's do it right here. Justification with the IVT is 1 point as well. So have to compare these values in some way and have to do the justification with intermediate value theorem. Now let's look at C. At time t equals 2, train A's position is 300 meters east of origin station, and the train is moving to the east. Write an expression involving the integral that gives the position of train A in meters from origin station at time t equals 12. Use a trapezoid sum with 3 subintervals indicated by the table to approximate the position at time t equals 12. So it's saying that we know at time t equals 2, let's say not t equals 2. Let's put it this way. We know that if x is the position, so position, that x of 2 is 300. Okay, we'll say the east is positive in this case. Okay? Well, we know it's moving to the east at that time. So that makes sense. Positive velocity means we're moving to the east. It's already in the east. We need an expression involving the integral that gives the position of the train. Well, remember, the position has to be the integral plus its starting position. So we can go ahead and get that part done. We know that it's going to be the position at 2 plus the integral from 2 to 12 of the velocity. That's a pretty easy integral to set up. Well, from there, it's much easier to see the trapezoid sum we're going to set up. Okay? So if we look at it, we have 300 plus, and then our trapezoids are going to be 2 to 5, 5 to 8, and then 8 to 12. Now, the problem is these do not have the same width. So you're going to have to make a trapezoid for each one of these. That part is going to be frustrating. So let's go ahead, let's just take this and let's write out our trapezoid sum over here. All right? So for the first one, we have to add our heights. So 100 plus 40, divide by 2, and then multiply by our base of 3. That gives us the first trapezoid. So this is from 2 to 5. That's not a good multiplied by 3. Let's write that differently. Let's put the 3 on this side. Okay, then we do from 5 to 8. Add our heights, so 40 plus negative 120, divide by 2, and then multiply by the width. Well, this one is also 3, so that makes it easier for us. And then for the last one, 8 to 12, multiplying by 4, this one is negative 120 plus negative 150 over 2. So that is going to be that little integral right there. That's our trapezoid. We're just making a trapezoid with each one of these. Okay? But now we have to actually solve it. And you will be asked to solve something like this. This is no calculator. So you're going to add all those, and you should come out to get negative 450. And so when we add it, we get negative 150. So let's think of this in terms of context, because we have to give this number context. We know it's a distance, so we know it's meters, but we were saying that positive is to the east, okay, because we're giving a 300 the east direction, and it's now negative. So this means train A is 150 meters west well, we'll say is approximately, because we approximated. 150 meters west of origin station at time t equals 12. Okay? A lot of work put into this one, but let's look at what we have. We have 1 for the position expression. So that's this part right here. All right? Now, I think you should be fine with this, but to be more specific, we should say S sub A of 12 is this, but then this part is approximately this. So we need to make sure we're saying this is an approximation and the actual, or not S, X, sorry, we're using X for position. So this equation right here is exact, but the integral itself we're approximating. So that part needs to be approximated. But 1 point for setting up your position equation. 1 point for correctly doing the trapezoid sum and getting negative 450. And then 1 point for a position statement for where it is at time t equals 12. So 1 point there. So 3 points here. So we've done 1 point here, 2 points there, 3 points there, which means that leaves 3 points for part C, or part D. So part D is saying a second train, train B, travels north from origin station at time t, and the velocity of train B is given by that velocity equation. At time t equals 2, the train is 400 meters north of the station. Find the rate in meters per minute at which the distance between train A and train B is changing at time t equals 2. So we need the rate which the distance between them is changing. Okay? So we need to create an equation for the distance between train A and train B. So I'm going to do it off the side in this gray space. We have origin station here. Train A runs east to west. We're just going to, in general, point it to the west. Train B runs north and south. So this is B, this is A. And then that part, we'll call it, we'll call it Z, is the distance between them. Okay? So let's think about, we want the rate of change of the distance between them. So we want dz over dt. Well, to get that, we have to use this equation. A squared plus b squared equals z squared. And so we end up with 2a dA over dt plus 2b dB over dt equals 2z dz over dt. Okay? And so to get the distance between them, we have we'll divide it by the 2. So we have a dA over dt. So the position of A times the rate of change of A plus the position of B times the rate of change of B over the position of Z. Well, the position of Z is just the distance between the two trains at that time. So let's try and get all this information. We're looking for the rate of change between them at time t equals 2. So let's go through and see what we need. We need A of 2. Let's see if we can find A of 2. A of 2. Nope, we're not given A of 2. We might have to solve for that later. Right now, we're not. We'll come back and see if maybe we're given something. We were given this right here. No, they didn't say that. Okay. Yeah, they want us to use this distance right here. They should have said that. This is a pretty poorly worded one on their part. So this, A of 2 at time t equals 2, the position is 300. We need B of 2. So the position of B at 2. Well, it tells us that straight away. That's 400. We also need z at time t equals 2. Well, that one we don't know, but we could solve it using the triangles. A squared plus b squared equals c squared. This is a 3, 4, 5 triangle, so that's going to be 500. Easy enough there. Now we need our rate of changes for each of these. We need the rate of change of A at time t equals 2. Well, that comes from the chart. That's going to be 100. We need the rate of change of B at time t equals 2. That's going to come from that equation they just gave us for B, the velocity of B. Well, we're just going to have to plug in 2 there. Oh, that's not great, but that's 4 times -5, that's -20, plus 120. So it seems like, if I'm correct, we're getting 125. And then the rate of change of z, well, that's what we're looking for. So let's solve it. We know A of 2 is 300 times its rate of change, 100. B of 2 is 400 times its rate of change, 125, over z of 2, which is 500. A little bit of multiplication and addition, and you should get 160 meters per minute. Okay? So, there shouldn't be a t there. So, let's look at how these points would distribute. The first point is implicit differentiation of the distance relationship. This is actually 2 points, and that is just this work right here. All of that work right there is 2 points. And then 1 point for the correct answer. So 2 points for making sure you get all this set up right. Even if you didn't know the values of some of these, like you didn't know that you had to go back and grab 300 from there, you could have gotten 2 points if you set it all up. 1 point for getting the correct answer. Okay, so in total that's 9 points. Make sure you give yourself a grade, and then submit it in the homework for FRQ number 5. Send me an email or message on Honest Learning if you have any questions. You have a great day.